S of f. Now, if you carefully observe, then you may have a question in your mind saying why there's a gap between the two spectrums. Now, this gap exists because we have taken sufficient gap between the two impulses in the second waveform. If these two impulses, that means 0 to fs, this gap was very small, in that case the shifting of the spectrum would have occurred in similar way. But you can see that if this fs was very much towards this 0 side, then these two spectrums would have been overlapping with each other. Similarly, this minus fs would have been towards 0 in that case also, and these two spectrum will also be overlapping with each other. Now, if that happens, then let us try to understand what will go wrong. Let's talk about recovery of the original signal back. How do you recover the original signal from the sampled version? All you have to do is use a low pass filter which will have the pass band only around this original spectrum. So if I can use a low pass filter with cutoff frequency FM, then it will select the original spectrum and it will discard all this newly generated unwanted spectrum from the signal, and we will obtain the original spectrum x of f and hence the original signal x of t. So the recovery of the original signal is possible from its sampled version simply by using a low pass filter. That is because the only difference between the original spectrum and the sampled signal spectrum is that there are unwanted frequency spectrum generated. We only want the original spectrum to be there and remove the unwanted spectrum. This can be done using a filter. But this filtering procedure will fail if the two adjacent spectrum are overlapping each other. Only if there's a gap between the two spectrum, I can use the filter and I can recover the original signal. And hence we conclude that the recovery of the original signal is possible only if there's a gap between the two spectrum. Now, when will there be gap between the two spectrum? If you observe, this point is frequency FM and this left hand side point is Fs minus Fm. So there will be gap between the two spectrum if Fs minus Fm is greater than Fm. If this point is greater than Fm, only then there will be a gap. Even if Fs minus Fm is equal to Fm, then these two points will coincide. There will still not be any overlapping and I can still recover the original spectrum and remove the unwanted spectrum. So this is the criteria that we must satisfy before we go for the sampling process. Let's take this once again here. So I repeat, the criteria that we have just derived says that Fs minus Fm should be greater than equal to Fm, and this turns out to Fs should be greater than equal to, we take minus Fm on the other side, it becomes twice Fm, and this is very famously called Nyquist sampling theorem. The sampling theorem must be greater than equal to twice the maximum frequency of the signal. So if Fm is, let's say 1 kilohertz, then it can only be sampled with a frequency which is greater than equal to 2 kilohertz. If you use any value less than 2 kilohertz as the sampling frequency, then the two adjacent spectrum will overlap and the recovery of the original signal will not be possible. Please remember that what we just now discussed is only valid when the original signal has low frequencies from 0 to Fm. Such type of signals are called low pass signals. This is called low pass signal. So what we just now derived is the sampling theorem for a low pass signal. I repeat, a low pass signal is the signal which has frequencies from 0 to some constant value Fm.